Nope.
Do you speak
Aren't those
Amish?
people like the Mennonites? Because I saw like.
Yes, but they really smell, I will say that.
They're talked to them.
Yeah, because at one time I saw an Amish person driving a board expedition. I'm like, this is wrong. Oh, they must be American.
Half in a bottle.
I don't exactly know.
Alright, hey, we gotta focus, it's a big day and a big chapter and a big life. So let's focus here, okay?
Wait, so this whole is not.
No. Yeah, but it is. But that, if you don't do it today, yeah, okay. Never mind. Alright, have you ever let a helium balloon go outside?
Yes.
No.
What
I was
happens?
so sad it floats
Raise
away.
your hand. What happens? Go ahead.
You give it to God.
Excuse you?
Okay, Trinity.
It floats away. It falls down.
It floats away.
I did that
Which
once.
way is away?
Up.
Okay.
I did that once.
Forever?
Well, until something happens.
Until it lands and
Okay.
kills the sea.
So,
Until it makes a little alien kid happen.
Until the
I did that one.
okay. So have you ever wondered what happens to that balloon?
Yeah.
Yeah. Flock of birds.
Is it like, is heaven just full of balloons?
Yeah.
That would be fun.
That's what. How else would it? They pop when the further up they go, the thinner the air is. So they get thin and thin and thin, and then they just.
Why would they pop if it's thin air?
Because of pressure, right?
Okay. So part of the stuff we're going to
Does it
talk
just like fall down?
eventually, either one of two things will happen. It will pop because of something I will explain in a sec, or it'll get to the point where the density of the balloon is equal to the density of the air and it just sits up there. Which, that's not the case. There isn't like a ceiling where you just got balloons just hanging out up there. Okay? That would be really cool though, wouldn't it? No?
Yeah.
Okay, anyways, okay, so what usually happens is it pops, and here's how it, here's what causes it to pop. You have, what you have when you've got a balloon,
That's so cute. You need a smiley face on
guys,
it.
what you have is you have gas particles in here, right? They're moving around in rapid random motion and they're colliding with the walls of the balloon. What is that doing?
You make it
Making it move. Go up.
No, that's not why it goes up in the air.
Okay. Oh, it's because helium is light.
What's happening? What am I trying to show here?
It's
Well,
yeah.
It's expanding to fill the container.
assuming I just have a balloon sitting here, there's gas inside the balloon that are colliding with the walls of the balloon, exerting a
force.
which exerts a
Pressure.
okay. Force over area is pressure. Okay. So what you have is you have pressure due to the gas particles on the inside. Well, we know that if there was no force or pressure exerted back on it, what would happen to that balloon? It would expand, right? Okay? But we know that there is air or atmospheric air that also is gas that could collide with the balloon and exert a pressure back down on the balloon. Does that make sense?
Yes.
Okay? This is why you don't see the balloon getting any bigger or any smaller after you tied it. But when you blow air into it, you're incorporating more gas that's exerting more pressure, and so it'll expand until it gets to equilibrium with the pressure that's exerted on the outside. Because as it expands, as we'll talk about in this chapter, when you take the volume and you increase the volume, you decrease the pressure. Okay? And we're also going to talk about the temperature impact of it. So what happens is, as it's rising in the atmosphere, what do we know about the pressure as you go, the atmospheric pressure as you go up in the atmosphere? It drops. Okay? So this pressure that's pushing inward is starting to get smaller. So now we're not at equilibrium anymore,
So
right?
the inside gas
So the
is
balloon
bigger.
starts to expand until it gets back to equilibrium. And then as it rises some more, this gets even smaller.
Whoa, so that's why.
Until eventually, it expands so much that it expands to the point where it cannot, the elasticity of the balloon cannot hold in the gas, and it goes kablooey, and then it does fall into the ocean and kill a turtle.
What about a weather balloon?
Okay? What?
Yeah, don't they like come back down?
I don't know what a weather balloon is.
What?
They send it out to like, yeah. They
Oh,
send-
that must be some sort of material that.
Can you draw a straight on the balloon?
No.
Yeah, please.
Okay. So, we're going to talk about the kinetic molecular theory today. So this whole chapter has to do with gases. Hey, can you believe we have a whole chapter to talk about gas? That's awesome. What jokes? Alright. Now, we're going to talk about the 6 postulates of the kinetic molecular theory that are used to describe the properties of a gas.
Do we need to know all of these?
You will need to know them well enough. You won't have to memorize them, but you're going to need to know them well enough to answer some questions, maybe write an essay question, who knows.
That sucks.
Okay? They're not overly difficult. Postulate 1, gas particles consist of very small particles, each which has a mass. Okay, this makes sense. Does this make sense?
Yeah.
So air has mass. Okay, so how do you weigh air? How do you weigh air?
What is like?
Atmospheric
Pressure? So there's like a thing with the weights and a string. No? What?
I don't know, I'm not sure what you're talking about.
Okay. I feel like there are different weights.
How do you weigh air? It's got mass, you gotta be able to weigh it, right? You gotta be able to find its mass somehow.
Well, I mean, pressure.
We just said that like 6 minutes.
I mean, that's a good guess.
Can I be the
Okay?
Yeah, because I just had a bunch of goldfish. It took me like 5 seconds.
Hurry. So, we know that to have a basketball, you gotta inflate it with air, correct?
Right.
Okay, is there any way we could figure out?
Oh,
Tanner?
measure the basketball when it's not inflated, and then when you inflate it, measure the basketball, and then you can figure out how much the air weighs.
Yes. Very good, Tanner. That was impressive. Good job. Okay? So, the difference with measuring the basketball without air versus the basketball with air would be the mass of the
Air.
air. Okay? Postulate number 2. Gas. Okay.
That's an interesting statement.
Postulate number 2. Gas particles are tiny compared to the great distances between them, and this leads to gases being really, really compressible. And I think I've shown you it. I'm not going to pull it out again because I'm pretty sure I've shown you the example of just taking a syringe and pressurizing the gas in a syringe. Syringe. Is that what is?
What? Well,
Yeah.
I thought a syringe was like, it sounded like a knife.
You need a scalpel? Pinched it?
Yeah.
Okay.
Something like that.
Anyways, the average, listen to this is pretty cool. The average distance an oxygen molecule must travel between collisions with another oxygen molecule is 20,000 times its own diameter. So you know we've talked about this before about how, okay, yes, but still, probably less than that actually. I don't know if you guys caught what Natalie said. She said, so what, they have to travel an inch? Which probably was actually quite a bit less than an inch because an atom is so small. Okay, but we have talked about how gas molecules are extremely far apart compared to their size. Okay, this is why they can be compressed very easily, and liquids and gases cannot be compressed. Okay? Nothing super crazy that you may not have known up to this point, right? Number 3, gas particles are in constant, rapid, random motion. This explains why gases immediately fill their container, because if they weren't rapidly moving and they weren't randomly moving, would they be able to fill their container? No, no. This is also part of the reason why when someone lets a big one go, you smell it.
Oh, okay.
Right,
That's
Natalie?
confusion first.
Okay, now it's not the only thing that causes it, but it's one of the things. You really have to have these 2 things for diffusion. You have to have gas particles moving rapidly and randomly, and you have to have space in between them, because is a gas molecule going to diffuse through a wall?
Well, I mean, it
Yes.
could.
No, that's called
very
effusion.
undense wall. Okay.
What if the wall is made of like,
Sponge?
Yeah.
Okay.
then you have a very.
Alright. Number 4. These are the next 3 going to be ones maybe you're not as familiar with. Okay? Particles do not interact with each other or the walls of their container except when they collide.
Natalie, hold on.
Okay, now listen to me very, very carefully. We're going to get into some gas laws later. Okay? Our gas laws are mathematical laws that we use to predict gas behavior.
Hey.
Ah!
Do you do this in every class or just mine?
Do what? Sleep? He sleeps in every class.
You tell him,
I
Tracy.
say like.
I swear, I don't know how.
You like biology more?
Oh, baller.
That was like DeMarcus Cousins' past.
Saw that.
That the JV game last night was a rough game.
Okay.
It was
Yeah,
good.
you did
It
put
was.
I'm gonna need to text your dad and see what your sleep habits are because you sleep a
Yeah,
lot.
about
Did
one
you
last
just
night.
play Fortnite?
Yeah, I'm wondering.
No, I did not. I did not.
How
Alright.
did you play?
Back on track, guys. Back on track.
I was up till 3, and I'm awake.
I was figuring out.
You do it every night, so you're probably used to it.
Maybe.
Okay, now listen.
Why not?
Can I explain this? Otherwise, you're gonna be reading the lesson. Because I'm not gonna waste a day because you can't focus. Okay? So, anyways, when I was talking about gas laws, those gas laws perfectly predict the behavior of a gas if this is true. And we're gonna talk about under certain situations this is not true. Okay, what this is saying is when gas particles come close enough to each other but don't collide, they don't interact at all. What do I mean? What I mean by that is they don't affect each other's motion. Well, we know that gas molecules have electrons and protons in it, so they do have charged particles in gas molecules, right?
Right.
So if they go by each other, is it possible that those charged particles could either repel or attract and cause their motion to change? Yes. But if a gas molecule is moving fast enough that when they go by each other, the attraction that they have for each other is so negligible because of how fast they're moving by each other. Does that make sense? Like if you took two magnets, we know they attract each other, right? And you went real fast. Would you notice feel any attraction?
Even if you don't notice,
Yes,
doesn't
I
matter.
would.
Well, it's considered negligible that it really wouldn't affect it at all. Yeah. However, we will talk about how if you change the temperature or reduce the temperature of a gas, now gas particles are moving faster or slower? Slower. So now they're going by each other slower, that the forces of attraction now do play a part. And we're going to talk about situations where this is true and where it's not. Some situations it's true, some situations it's not. Right, Gage?
Yeah, I was thinking.
No.
Do is like a really cold gas, like when if you have like really cold gas, you like fill up with a balloon, would like go like slowly.
Slower. Yeah.
What would happen if you filled the balloon with liquid
Explode.
nitrogen? That would be.
I would probably, I don't know,
That'd be.
probably freeze the balloon. I don't know. Okay.
I'm sure there's
Number
like
5.
50 million freeze of rubber.
Collisions between gas particles and their containers are perfectly elastic. What this simply means is when collisions happen, no energy is transferred, which this isn't always completely true either, but we're going to stay on the extreme side of things so that the math becomes a little bit easier. Okay, and you'll see why as we progress. Okay? Okay, the average kinetic energy of gas particles is directly proportional to the temperature. Why does that make sense?
Because the
What?
hotter it is, the faster they move.
Okay, what's the definition of temperature?
The amount of kinetic energy. So
Close.
movement, the average. Oh,
The average kinetic
That's what I
energy.
said.
You said amount.
Oh, okay.
Okay? Now, let me show you a little visual here.
Is this?
If you want to stand up and come over here, you can.
Oh.
Oh, shoot.
For.
I gotta do this really quickly. I'm not 100% sure it's gonna work. I don't have a lot of water. Come on, stand up. Come over here. Alright.
Maybe if we move so quietly.
Well, that's just water in there. I'm not sure if it doesn't work, I'll show it to you tomorrow. There's not enough water in there that I'm afraid it isn't gonna work. Trinity.
What?
Huh?
I have no idea what just happened at all.
Yeah, I didn't really see that.
Can we do it again, please?
Was that hot water?
I just crushed the can.
Damn.
Oh, you're so
You
strong.
heated
I
up
didn't
the
see-
gas part.
KJ,
You
no
heated it
way.
up, and when the hot air went into the cold, it compressed, and
Very good.
Wow.
Have a seat, guys. I'll explain this because I don't know if you guys were able to catch what Tanner said.
pretty neat.
Okay, it's very similar to this example right here.
Thanks,
Okay? Now, I'm going to use this example to kind of explain what's going on here and why the can just all of a sudden just appeared to miraculously crush. That's not a great little can drawing. But, okay, so what I had was water at the bottom of this, just very little bit of water. And I was boiling it. So what was happening is the water was starting to what? Evaporate, okay? Well, then there was gas inside the can. We know gases exert pressure because of their rapid random motion, so the gas inside the can was exerting a pressure outward inside the can, right?
Right.
Okay? Well, we also know that the reason why the can doesn't do anything is because there's atmospheric pressure that's equal and opposite, so that there's really no net force. Does that make sense? Okay? Well, when I took it and I inverted it into a cold water reservoir, all this gas condensed, leaving no gas inside the can. And so what happened is the pressure that was exerted by the atmosphere outside the can was so much greater than the pressure that was exerted inside the can that it what? Crushed the can.
That's like what would happen if you went to the bottom of the ocean, right? You wouldn't be able to,
Yes.
wouldn't be able to push it up, so.
Yep, the internal pressure that you have pushing out of your body would not be enough to overcome the pressure of the weight of the water on top of you that you would implode. Yes.
I like that.
Yeah, you're right.
Funny to watch.
Let's try it out.
Maybe when I'm like 85. and-
I don't even know if they've come up with something strong enough to get down to the bottom of the ocean.
Well,
Close, but not.
Close, but still. Close isn't the bottom.
Well, okay, never mind.
What's the matter?
That's all a block of steel.
What, Maddie? Say
Well,
that.
if you're on the beach and you walk in the ocean, aren't you on the bottom?
Wow. I've touched.
Yes, you're right.
I like that.
Did you understand what I was trying to say when I
I've been to
said
the
bottom?
bottom of the ocean.
She understands she's being so, oh my soul.
No, I know.
Crippling
She's
is-
acting like. Okay, diffusion, you guys are pretty aware of this. Spontaneous uniform mixing caused by particle motion. This occurs because gas particles are in constant random motion. And because of what?
What I was.
What's the matter? You did.
Because particles go from high up to low.
That's no.
Well,
What's the other postulate that you would have to have for diffusion? They gotta be rapidly moving.
Space.
Don't interrupt.
Yes, thank you, Maddie. You got space in
I
between.
didn't hear you the first.
Or you're not going to be able to get in or through, you're not going to be able to diffuse through the air. So when bacon is sizzling on the pan, you can smell it because gas molecules coming off the bacon are diffusing through the air and into your nostrils. Okay? Effusion is the process in which gas particles pass through tiny openings, or I think your book uses the word orifices, okay, into an evacuated chamber or space. A very, very common example of this is what happens to a balloon over time.
Oh.
What happens to a balloon? I was always dumbfounded by this when I was a kid.
It gets smaller.
Yeah, like the balloon is like this cool balloon, all of a sudden it's like shrivelly and boring. I mean, where the heck did this gas go?
It's like people.
It infuses out of
What?
shriveling and boring.
Over time.
That's true. You shrivel up and get boring. Yes. My mom and dad were here this weekend. My dad slept like half the time. Like, keepers, I don't want to get old. Okay.
My parents are 40.
My parents are my grandparents are
Okay.
like 60.
So effusion is this idea that even though solid particles are heavily compressed or compact, there still is small gaps in between them that if you had a tiny particle, it could eventually work its way through.
Neither of my parents are.
Okay? This is partly why we cannot use hydrogen gas as a fuel source because it's very difficult to transfer, because it's such a small molecule that it can wiggle itself into the solid structure of big tanker trucks. And believe it or not, hydrogen gas weakens tanker truck steel. And you wouldn't want a truck going through and all of a sudden it just completely cracking and breaking and letting a whole bunch of hydrogen gas out into the atmosphere.
You just need to make completely solid tank.
Yeah!
What if you put
What if you put
helium
helium
in
in your
your
car wheels?
What would happen?
They would float.
I feel like the weight of the wheels
Yeah.
would.
No, but like, would
You
that,
wouldn't get any
no,
traction.
but would that work as normal, like,
Probably. You probably wouldn't notice anything, to be honest, because it's not going to have enough.
that's how we get plain cars.
You might have less.
No, that's
You might have less
wheels.
friction. That's it.
Because I wanted to put like helium in an air mattress once. So like,
Oh,
That
that's
would
like
weigh
a
hydrogen.
bunk bed, but
Okay, hydrogen mix. Hydrogen gas. I'm
Until
not.
you
but I feel like
It's like,
yeah, you
you
get
wouldn't
on
wanna.
it.
get out of bed and just
It's
go
like-
to the ceiling.
Alright.
Go to bed and go.
Show all your blankets and pillows and stuff on it.
So we're going to talk about Graham's law of diffusion. Do you have an equation in here or no?
Until you get a leak and you start breathing.
All right, here's Graham's law of diffusion for you.
Guys.
Rate 1 over rate 2.
That's an upside down L. The rate, that does not look like an R. Well, okay.
There's your equation for Graham's law of diffusion. What you can make of this particular law is that the smaller the particle, the more it diffuses. Why does that make sense? Why does it make sense that the smaller the particle, the more it diffuses?
It's smaller so it can fit in the gas station.
Yes, it's not rocket science.
I have 0.
Guys, it's
Rocket science.
is it?
Whoa, rocket science.
That's why quiet farts smell worse.
That doesn't make any sense. Particles are smaller.
What'd you say, Brian?
I said that's why quiet farts smell worse than the loud ones. Because the rate of diffusion is faster.
On quiet ones or loud ones?
What?
How do you know that? Small farts. Big bubbles versus little bubbles.
That's
Or
exactly
maybe
how it
the
works.
energy is being diffused in sound instead of smell.
What smell it?
That's totally a false statement, but I just wanted to
Smell energy?
say.
That's a new science.
Smell energy. I'm gonna go and prove it, guys. There's such a thing as smell energy.
Alright, you do that, you make $1 million off of that.
I'm gonna spend my entire life discovering
Okay, so here's what this is saying. The rate of a gas diffusing is proportional to its molar mass. Okay?
Oh, that's funny.
How is that? What is
M is molar mass. Yes.
First I thought your Q was a Z, so I had to cross it out.
Oh. Okay.
I thought it was a Z too.
Thanks, Mary.
Z.
Oh, that's a 2?
Z, you thought it was a Z?
Rate 1, rate 2, molar mass 2.
Rate C, rate 1.
No, but then I looked at the bottom, I was like, oh, okay.
Guys.
Well, your other 2 is a
You're the
different
same
one.
students that if I gave you the wrong page in your homework, you would do it.
That's gay!
I would
What-
not. I don't do it anyway.
Well,
How dare you insult him, Kramer?
Me?
He doesn't do his homework.
Yeah. Sorry. Okay, so it says calculate the ratio of diffusion rates between nitrogen and argon gas. Now here's something you might want to write in. Your heavier molar mass is going to be the one that goes on top. It just keeps it so that your ratio is above 1. So I'm assuming you will be able to do this. So this would be your rate ratio if I had the whole thing. Does that make sense? So which one has the heavier molar mass?
Argon.
What is it?
Argon.
Okay, but what is its molar mass?
Oh, 39.95.
You guys haven't already forgot how to do molar mass, have you?
We have not, but I don't have the periodic table, and I can't see that.
12, no, 14.0.
28.02.
Oh. Ah!
Are you a sheep now?
Come on.
Equals your rate ratio. Why don't you guys solve that? Yes, bring your calculator.
No, I have one right here.
Okay, we're gonna be doing like 8 different rate gas law equations, so you will need your calculator this chapter. You will have to remember all of the rate laws and the equations, because I'm not giving it to you, so you'll have to memorize it. That's nice.
What do we add it to?
Since these are molar masses and those are constants, I'd be fine just rounding it to 2 decimal places, or 4. I don't really care. I'll be honest. Do what you want.
I had a dream that my calculator lit up.
What do we
It's like bright. It doesn't have like LEDs or anything.
Okay.
My dream was like,
What is this for?
It's from Moana, the short film before it.
Okay.
It's,
What do you guys get?
are you sure?
What do you guys get?
Okay. I think, oh yeah, you're right, you're right. It's 1.9, or 1.1.
I got 1.9.
I got
1.19.
Yeah, that's right. That's what I was
I
trying.
forgot about square roots. I don't know what those are.
Okay, so let's make sense of what this tells us. Anyone have any idea what this tells us?
which one do you
The rate ratio.
Okay?
No.
Yeah, it does tell you the rate ratio, but what this is telling you is that your nitrogen gas is going to effuse 1.19 times faster than your argon gas. And why did I say it is the nitrogen gas that's going to effuse faster?
Because rate 1 over rate.
Well, it's nothing to do with which one's rate 1, which one's rate 2. It has everything to do with the size. Okay?
So is there a unit?
The grams per mole actually will cancel out, so it's a unit. It's a ratio of its unit. Almost all ratios are unitless.
That's also upsetting.
Okay, here's some more vocabulary words, although I think you're pretty familiar with most of them.
Vermilion.
Whoa, don't say that.
Revenue.
What is
Okay, so quickly, I know you guys know most of this.
Oh shoot.
What? Permeability, it's basically, so we talked about effusion. This would be measuring how much. Okay, you guys have heard back in physical science that both gases and liquids are fluids. Why can we call them fluids?
Because they move freely.
They are fluid.
But
Because they have the ability to flow. Okay. Solids are not a fluid because they do not have the ability to flow.
I'm a solid, I'm a fluid.
Is water wet?
Well, just, okay. Well, just let him finish, we can go.
Okay, compressibility, you guys know what that is?
Yeah.
And expandability, I feel like you're pretty familiar with
What's the
that.
whole word?
Is water wet?
Water wet. If you're not attracted to water, you will never get wet.
But are other water molecules attracted to water?
Yes, so water molecules are wetting other water molecules.
So is water wet?
Oh,
Because it's just your pen was still on.
Making the other molecules what? Then
Yes.
therefore
Because
it's
it's, if molecules are making other molecules wet, then the whole is wet.
Water molecule by itself is not wet.
Water's not wet.
Wait.
Okay, water's actually not wet.
Water molecule by itself is wet.
But
No, okay, so water is wet. No, okay, so no, well, listen, I used to think that water wasn't, was wet because obviously.
No, please, I do not want you writing on the board. I'm done.
No, dude, the act of being wet is something that has water touching it, that makes it so that it can't.
I'm literally not
So
listening.
that makes it that the water
I haven't heard a word.
Water cannot be removed from
I was
water.
actually listening to Craig.
No, I mean,
Water's actually not wet, okay?
If you're immersed in water, are you arguing about something?
Okay, we gotta get going real quick today.
Real.
Well, if you're immersed in
2
water.
minutes, sit down.
I pray that we just argue small things in life that don't matter. And I was like, J-Car, shut up!
Whoa! What?
Someone's tilted.
Oh,
Jump towers. There are other times I'm like, why is it?
that was a Fortnite joke. It's Fortnite.
Hey, today is one of the more complicated lessons, so you have two choices. You either waste time and talk, and you read it on your own and learn it by searching YouTube videos, or you don't waste time and you focus and you let me kind of try to tell you. Which one do you want to do?
Amen. Whatever one you want to do,
So,
Craig.
homework out. Bell ringer is on the board. Go ahead and start that.
Actually, the main Yes. You were saying 3 inches, my jet engine, would that be louder or shorter? Louder or quieter? You heard me.
I said the word wrong.
It's like jump ropes.
What's that from?
What's that from?
I saw it.
Wow.
It's gonna be much.
The first time I got Snapchat, Chris Pitt started a streak with me the first day. And it was a picture of chickens.
No.
No, I didn't even respond to it.
Oh, why are you doing one red?
Wow. No, I didn't leave one red. I read it. I just didn't respond.
That's
No! That is a faulty way of explaining it. You think I don't know? We know. Stop! We're gonna change that word and we're gonna call it unresponded.
That's what I said.
It's the dumbest thing to say unread.
Like when they look at their phone, it says they read.
and then you didn't
Like,
respond.
you
So
read
left them on red.
the message. As in,
On red.
yes, you want him on
You mean
red.
on red, the color red?
No.
On read? I already left them on read.
No.
Don't say I read it. That's
You didn't even look at my
On red, I just opened it.
I was that's a one
He
page.
said I read it.
I read it in a
That's going in the crate.
I'm
looking around.
Didn't leave it on red. I just opened it and didn't respond.
Stop! You guys are so mean.
That's all the facts. I would have been okay if you would have accepted that's what it was, but then you're like, no, that's not what it is.
Defending yourself kind of.
Okay, let's go. Homework. I'm keeping us on track. Hey, one more
Let's
time.
start that. Take a picture of my toilet and send it back to them.
Thank you, Craig.
Okay.
Crusty, but it's here.
Homework to save time, is there any specific questions you have versus having me go through the whole assignment?
Five.
Just the last one.
Number one,
Yeah, 5.
460.
I have questions on every single one.
Is this the last? I have 12 questions on it.
Child abuse.
Yesterday you said you beat me up, and that was on.
yeah, but this is from